In this and the next video, we'll be examining the time response of higher order systems. So these are systems where the denominator is order greater than 2. We've studied the first and second order systems already, and what we'll find when we study the higher order systems is that often they'll act like first or second order systems. So let's begin this analysis by looking at a simple higher order system, actually one that is second order. So we have a transfer function g of s, which relates the input x of s and the output y of s. And this transfer function g of s, as given here, has a pole at -1 and a pole at -50. This is an overdamped second order system. Now what I'm going to do is I'm going to divide the top and bottom of this transfer function by 50, and then we'll find g of s is 2 over tau 1 s plus 1 times tau 2 s plus 1, where tau 1 is 1 over 50 and tau 2 is 1. And so this is in a form which makes it clear what the time constants of the two poles are. The time constants are tau 1 and tau 2. These time constants say how quick each of the poles is. So one of the poles, the one at -1, has a time constant of 1 second, and the pole at -50 has a time constant of 1/50th of a second. That means that that pole, the one at -50, is much faster than the pole that's at -1 in terms of the response. Faster because the time constant is smaller. So we'll take this system in second order time constant form, and we'll break it up into two systems, G1 and G2, both of which are in time constant form and are first order. This is shown in the figure at the bottom of the page here. We have the input x of s going into G1, producing signal v of s, which goes into signal G2, producing y of s. And you'll notice G1 has got the pole at -50, while G2 has the pole at -1. G1 here has got the fast pole with the small time constant, and G2 has the slower pole with the larger time constant. So with our overdamped second order system broken up into two subsystems, we're now going to look at how the internal signal v of s responds to the signal x of s, and how that v of s then produces signal y of s. Let's now look at what the internal signal v of s looks like when the input to the system x of s is a unit step. So v of s will be equal to 1 of s times x of s, and x of s is 1 over s. We find after we inverse Laplace transform that v of t is 1 minus e to the minus 50t times u of t. And so what that means is that in response to a step input, that v of t rises up to an output of 1 and does so quite quickly, in about 0.08 seconds. This is a very fast response, and it's shown here at the bottom of the page. So we have this signal v of t, which very quickly rises up to a value of 1, does that in 0.08 seconds, and that v of t is now going into our second system, G2, and G2 has a time constant of 1 second. So G2 is slow, but its input is rising up quickly. So what will the output of G2 be when v of t is like this? So here's the way I want you to think about. The signal v of t rises up to a value of 1 very quickly, much faster than the time constant of signal G2 into which it's going in. From the point of view of G2, this signal v of t looks like a step input. It happens so quickly, rising up to a value of 1, that from G2's point of view, it seems as if it rises up instantaneously. Since the input to G2 looks very much like a step from G2's perspective, we can expect the output of G2 y of s, the response to v of s, to be very close to the step response of g2. Therefore, we see that the step response of the system g of s, the second order system, is essentially the same as the step response of g2, a first order system. That is, system A, shown here, acts like system B, even though system B is of lower order. So the lesson of this example is that sometimes a second order system can be approximated by a first order system. This lesson also holds for systems of higher order than second order. Sometimes they can be approximated by second order or first order systems. Let's look again at the poles of the system g of s. We had one pole at -50, and it had a time constant of 1/50th of a second. And we had another pole at -1, and it had a time constant of 1 second. The pole that's far to the left at -50 corresponds to the fast dynamics of the system, fast because its time constant is small, while the pole at -1 corresponds to the slow dynamics of the system. This pole at -1 is the one that dictates how the system responds to a unit step, so it's referred to as the dominant pole. It largely determines the step response of the system. Once we realize that g of s acts just like g2 of s from the point of view of a step response, then we can simply find the step response of g2. And that's easy enough to do. We've studied how to find the step response of first order systems. You'll recall that the step response of a first order system goes to the DC gain in a period of time equal to 4 times the time constant. Now, for our system G2, the DC gain was 2, and the time constant was 1 second. And therefore, we know that the response of G2 to V of t will look like the signal shown here. This same idea can be applied to higher order systems. So let's now consider a third order system, given as g of s here. This system has one pole on the real axis with a time constant tau1 and a pair of complex poles that are underdamped, which have a time constant tau2 equal to 1 over zeta omega n, where omega n is the undamped natural frequency of the poles and zeta is the damping factor. As before, we're going to break up our system g of s into a fast and slow subsystem. Let's suppose, as before, that tau1 is much less than tau2. That means that g1 has fast dynamics and g2 has slow dynamics. That is, the second order system has the dominant poles. The first order system, the one with the pole at -1 over tau1, has the fast poles. Now we're going to use the same logic that we used previously. We'll suppose x of s is a unit step signal going into the fast dynamics G1. Then the output V of s is going to look like a unit step because it's going to rise up to a value of 1 very quickly. It'll rise up in a period equal to 4 times the time constant of system G1, that time constant being tau1. Since the second order system dynamics have dominant poles in this example, the third order system g of s will respond like the second order system g2 of s when a unit step is applied as input. So we can expect the output of the third order system to look like a typical second order system output, and that's sketched here, y of t. The overshoot and settling time for this response are dictated by the placement of the dominant poles in the complex plane. Now, in the example we just did, the second order dynamics were slow and the first order system's dynamics were fast. So now we're going to reverse that. Let's suppose the second order system dynamics in our example are faster than the first order dynamics. So tau 2 is much less than tau 1. In this case, the third order system will behave like a first order system when a unit step is applied as input. At the top of the page here, I've sketched the pole locations for this example. We have the second order dynamics as fast with the time constant of tau 2, and these are underdamped poles in the left half plane. The dominant pole is the one closer to the origin. It's the one at -1 over tau 1, where tau 1 is the slow system's time constant. In this case, the response of the third order system will look like the response of a first order system. That is, it will go to the DC gain of the system in an amount of time equal to 4 times the time constant of the slow system, and it'll do so without any oscillation. Not surprisingly, we can extend this idea to even higher order systems. So let's consider a fourth order G of S, shown here. And this fourth order G of S has got pairs of complex poles, one with a time constant of tau 1 and the other with a time constant of tau 2. The one with the time constant of tau 1 are the dominant poles, while the ones with a time constant of tau 2 are the fast dynamics. So in this example, the fourth order system will respond to a unit step in the same manner as a second order system. It will act like the slow dominant dynamics, the ones with the time constant of 1 over tau 1. So the response will be a nice second order response with the overshoot dictated by the damping factor zeta 1 and the settling time dictated by the time constant, or the real part of the complex poles, the settling time being at 4 over zeta 1 times omega 1. So I want you to reflect a bit about what we've learned in this lecture. We've learned that higher order systems will often behave like first or second order systems, with this behavior dictated by the dominant poles, the slower poles of the system. In our next lecture, we'll extend this idea to a few more cases. But first, I want you to think more about what we've learned, that higher order systems can behave like simple first or second order systems. This should not really be that surprising if you think about it, because in reality, all the systems that we study, mechanical systems, are not really first or second order. They may behave like first or second order systems, but in reality, they're not. If we had an actual second order system, a mass spring system, sitting in our laboratory, we would find it's really not second order. Why? Because our spring really has some inertia to its elements. It's not massless, and therefore it really is a higher order system, although we can model its response as that of a second order system.